So the idea that people have arrived at is the following one. The Big Bang produced equal amounts of matter and antimatter, and early on, when the universe was just a fraction of a second old, what was happening was the matter particles were meeting antimatter particles and annihilating each other. There had to be some asymmetry in the early universe so that in all those annihilations, there was a little bit of a balance tipped in terms of what we call matter rather than antimatter. It actually doesn't have to be much of an asymmetry. It turns out that we only need the annihilations for every, say, 10 billion antimatter particles. You only need to have about 10 billion and one matter particles. They all destroy each other, and the one guy that's left over, the matter particle, in those collisions, those particles are what form all of the matter that we see in the universe today. That's the idea that we currently have for what happened in the first instant of the universe. So there was a lot more matter around. We now see it in terms of a rather cold glow of photons floating through the universe. We call it the cosmic microwave background in technical jargon. So this asymmetry, there must have been an asymmetry in the laws of physics. So maybe this is related to these guys, Nambu. These guys, Kobayashi and Maskawa's work. And indeed, we can see those sorts of asymmetries when we do high-energy experiments in modern accelerators, like this one in Japan, which some people here in Sydney are working on. That bangs together matter and antimatter, electrons and positrons. And when it does that, these are just pictures to show you how big it is. Okay, it requires a rather large detector to catch all the stuff that comes out when the positrons and electrons annihilate, destroy each other. And what this accelerator does in those collisions, it produces equal numbers of matter particles and antimatter particles, which are called B mesons. They're like a heavy cousin of those kaons we met a little while ago. They're a bit heavier, they live for a shorter amount of time, and they contain a heavier quark and antiquark. And the experimenters study how those things fall apart. And do the matter particles behave in the same way as the antimatter particles? The answer is not quite. Not quite. This is the results of that experiment, published in 2001, and there was another experiment. This was considered so important. There was another experiment on the other side of the Pacific, in California. Both of those experiments found the following thing, that the matter particles fell apart in a different way to the antimatter particles. I don't really need to explain this graph to you. All you need to take from this picture is that if matter and antimatter behaved in exactly the same way, then the blue curve here would lie on top of the red curve. But you can see how they're offset. Or equivalently, this funny sinusoidal curve here, the red curve, the black points of the experimental data, would be flat. So this rather beautiful result showed, in fact, that these particles also show this matter-antimatter asymmetry. And what's more, the amount of matter and antimatter asymmetry that these experiments found was exactly consistent with the theory requiring 3 generations of quarks and leptons that Kobayashi and Maskawa invented. And so this was the crucial experiment which then showed that their idea was right and gave them the Nobel Prize. There's only one small problem. It's a beautiful theory, that Kobayashi and Maskawa have helped us develop. Great effort. The trouble is, it can't explain the evolution of the universe, the amount of matter-antimatter asymmetry we see in the universe when we look out today. They almost got it right. They're only a factor of about 100,000 out. Still progress. It turns out that whatever is causing the matter-antimatter asymmetry, this CP violation that we've talked about, there must be another source of it going on in the early universe than the one that we've seen works in amongst the particles that we already know about. So the quest continues to try to find experimentally, perhaps new particles which would help us along this quest. But their work has helped us in some way. We're getting on towards when I should be wrapping up. I haven't yet explained to you what this other fellow Nambu got his half of the Nobel Prize for. Nambu got his half of the prize for this idea of spontaneously broken symmetry. You actually have this concept in everyday life, although you may not know it. Imagine you've got a pencil. So you stand your pencil on a table and you let it fall, and it falls in a particular direction. It's not stable. If I do it again, it falls in a different direction. Okay? So hard as I might try to balance that pencil on its end, if I let it go, it's not in a stable situation, and nature chooses to make it fall over, but it breaks the symmetry. When it's standing up like this, you have a perfectly symmetric situation. When it falls down, nature chooses a particular direction, and we call that spontaneously breaking the symmetry. It wants to fall down because it gets into a lower energy state. And nature tends to seek out the lowest energy state available to it. So when it's lying down, it's in a lower energy, stable state. It's not going to fall any further. Okay? That basic idea has found its way into the fundamental laws of physics. Now looking at the equations that govern the fundamental laws of physics. And Nambu introduced this idea to particle physics around 1960. He was actually studying something entirely different. He was studying a branch of physics which is called condensed matter physics. He was interested in superconductivity, which produces these neat effects like levitation of small amounts of material like this, or allows for very huge currents to flow in wires with very little resistance. But the ideas he was studying to try to explain those sorts of effects, he then took over to talk about the equations that describe the fundamental physics of particle physics, and indeed our ideas of the vacuum, what we call the lowest energy state that we get if we took all of the particles out of the universe, what would be left. So just this idea, taking one area of physics, taking this idea that perhaps what happens in nature is that nature had an infinite choice as to how to configure the lowest energy state of the universe and chose just one of them. This idea of spontaneous symmetry breaking got us a long way to understanding the fundamental laws of physics. It wasn't actually Nambu that sort of nailed this, but it was Nambu who got the idea going. And then his work led to other people pursuing this idea and ending up unifying, just in the way that Maxwell had done, unifying the electromagnetic and the weak force. Maxwell had done it for electricity and magnetism. These guys in the 1960s unified, using this idea, the electromagnetic and the weak force. The guy who gets the credit from that, although there are actually three guys who did a lot of this work, is Peter Higgs, a very unassuming theoretical physicist from the University of Edinburgh, who's a little bit embarrassed by all the fuss and the fact that everybody is looking for his famous particle. In pursuing this idea of nature breaking the symmetry, required the introduction of a new particle into the basic theory, that particle or a new field pervading the universe called the Higgs field, and a new particle which is called the Higgs boson. It's that one on our fundamental building blocks picture that we saw at the start of this talk, which is still missing from the model. But the funny thing about the appearance of that Higgs, which results from the ideas that Nambu introduced, that we need to have it in the model, was amazing because it actually explained why particles have mass, why those force-carrying particles responsible for radioactive decay have a mass, and why other things like the photon don't have a mass. An understanding of that arose from the work of Nambu and then Higgs and others. So the idea is that those of you who have heard of the ether before, going back to the 19th century, this sort of ether throughout the universe, another one has been invented. It's a different sort of one. But it has the idea of something pervading the universe which has associated with it a particle called the Higgs boson. When other particles try to swim through this Higgs field, they're retarded in some way, and we interpret that retardation as the mass of the particle. That's the idea that these theoretical developments give us. And the fact that it was able not only to explain why some particles have mass and others don't, it was able to explain some of the relationships between the masses, but not all of them. That was a very productive line of research, and Nambu, having started it, gets the credit with the Nobel Prize. So we're led from this spontaneous